Okie dokie. I think that should be working. So hello everyone. I'm going to do these IYGB papers. I was going to do them for all my students, so I thought I might as well stream them. So that if anybody else in the future needs to do the papers or is revising with them, they have kind of full work solutions here that they can watch back on and figure out what's going on with all the questions. Let me just double check that everything's streaming live. Yes, it's coming up. I went live earlier while being on private, which is not useful, but it looks like everything's working correctly. So yeah, the papers themselves, they're meant to be like quite hard papers. I don't know if they're all A-star questions, but they're all going to be on the harder end of things as they go. You're meant to get 2 hours, so we'll try and get the whole thing done in this one slot. But we're in no rush, if it takes me a bit longer, So let's have a look. Question number 1. We've got the straight line L1, passes through the points 320 and 13, 0. L2 has a gradient of a third and passes through the point 0, 5. D is the intersection of L1 and L2, and we want to show that the length of AD is k root 5, where k is an integer. So first thing we'll need is the equation of the lines for both of them. So for L1, we need to work out the gradient. So thinking, what is the gradient going to be? Difference in y is ever different than x is. So as we move along from the 3 to the 13, we've gone along 10. So it's going to be something over 10. And for the y's, we can see that we've dropped from 20 down to 0. So it needs to be 0 take away 20, i.e. minus 20, to give us a gradient of minus 2. So that would be minus 2 for the gradient. The next bit then is to work out what the c is going to be. So thinking about this, if we're taking 2 steps down, every step to the right, every step to the left, we're taking 2 steps up. So if we need to take 3 steps to the left, that's going to be 6 steps up. So 6 steps above 20 is going to give us to 26. Same idea for L2, but L2 is a little bit easier. We've been given the gradient of a third. And if you look at point C, the x coordinate is 0. So the 5 we have there is just a plus c, so i.e. plus 5. So both of these should be y equal to as well. Just move that over a little bit. Next then, what we want to do is find the intersection. So setting these two equal to each other, basically, like simultaneous equations. So we're going to have that the third of x plus the 5 is equal to minus 2x plus 26. So adding this over, 2x and a third of an x is going to give us 2 and a third, i.e. 7 over 3, lots of x. 5 and 26, so do 26 take away 5, gives us a 21. So x itself, divided by 7, will give us 3, times by 3 will give us 9. So that's the x coordinate of D. To find the y coordinate, we can plug it into either equation, doesn't matter which one, because like we say, it lies on both L1 and L2. So this one's a little bit easier to deal with. A third of 9 is going to be 3, plus a 5 will give us 8. So that tells us that D is equal to 9, 8. That's the coordinates of D. A itself was at 320. So we just need to do Pythagoras to find the difference between these two, and therefore the distance between them. Difference of 3 and 9 is 6. Difference of 20 and 8 is 12. So we need to do 6 squared plus 12 squared, and then square root the whole thing. That over a little bit. So 6 squared, 36. We can be a little bit smart here, actually. So thinking about this, what have we got? 6 squared plus 6 squared times by 2 squared. So we can actually factorise that 6 out the front. Where it's a square root, it will get square root as well. And then inside the square root, all we're left with is 1 plus 2 squared. So i.e. that's going to be 5 inside. So the answer should be 6 times by the square root of 5. So what we can see there, our k should be 6. Lovely jubbly. Let's just move this up a little bit, not to encroach on the second question. So let's go down. What else do we have? The figure above shows a quadratic curve and a straight line with respective equations. Y is 4 minus x squared. Y is going to be 2. The points A and B are the points of intersection between the quadratic curve and the straight line. Find the coordinates of A and B, and then later on find the area between the two. So first of all, how do we find the actual intersection points? Same as we did up here. We have the two equations of the lines, set them equal to each other, and solve for x. So doing that, we'll take the 2 value, basically set our equation equal to 2. So we're going to have 2 is equal to 4 minus x squared. It's a bit easier to solve when our x squared is positive. So I'm actually going to add everything to this side. So we're going to have an x squared plus an x, and then take away 2 equal to 0. And if we go to factorise this, what we're going to have is x in both brackets to make the x squared. And then we need to make minus 2, like times together to make minus 2, add together to make positive 1. So we need a positive 2 and a negative 1, meaning the coordinates of A and B are going to be minus 2 and 1. And you can see A is less than B, so on the left-hand side, B is in the positive side of x. So this must have coordinates of 1, this has coordinates of minus 2, with both having the y coordinate of 2 that we already knew. So that's the 3 marks there done. So finding the actual area of the 2, we need to integrate between minus 2 and 1. So let's set that up. We want the integral from minus 2 to 1 of the top graph, take away the bottom graph. So we need this bit, take away the 2. So instead of having a 4 in there, we're going to have 2, take away x squared, all integrated with respect to x. When we integrate then, all of these are just simple polynomials. So we're just going to raise the power of x and divide by that new power. So doing that for the 2 gives us a 2x. For the x, will give us x squared over 2. And for the x squared, we will get x cubed over 3. Both of these then, we have to plug in 1 and minus 2. Plugging in the 1, nice and straightforward, just add up the coefficients. So we're going to have 2 minus a half minus a third. And then we're going to take away when we plug in minus 2. So this will give us minus 4. In this bit, minus 2 squared is 4. Half of that is 2, so negative 2 altogether. And looking at this bit, when we have negative 2 cubed, that will give us negative 8. So negative 8 thirds, and then the negative there will make it positive 8 thirds. We can simplify some of this stuff down. So what do we have? Maybe looking at the numbers first. The bits without the fractions, basically. So over here is minus 6. We're going to add that on, so it's positive 6 now. So 2 add 6 is going to be an 8. The thirds, we've got a negative third, and then over here, negative 8 thirds. So altogether, negative 9 thirds, which is just negative 3. And we've also got take away a half as well. That just carries over. No other halves flying around. So 5, take away a half, we should be left with 4.5, or 9 over 2. Lovely jubbly. Another quick 8 marks. That's the end of that page. Let's go to the next one. So what do we have here? Circle with a centre, a circle C with a centre at the point P. Radius R has this equation. Find the value of the radius and the coordinates of P. So to do this, we want to complete the square for x and for y individually. So look at the x bits. You've got x squared minus 8. So that's going to become x minus 4, where the 4 is half of the 8. That whole bracket gets squared, and then we take away 4 squared. So that's, imagine we just had the x parts. That's completing the square form for the x. Let's do exactly the same thing for the y's. So half of 2 is 1. So we're going to have y minus 1 all squared, minus a 1 squared as well. And this does still equal the 0 that was on the other side of the equation. The last step then is just to combine these numbers together and bring them to the other side. So thinking about that, we'll have the x minus 4 still all squared. The y minus 1 all squared is still there. 4 squared is 16. 1 squared is 1. Add them up, you get 17. So we'll add that to the other side. And this then is the general form of a circle, where we can see we're going to have a centre of 4 and 1. Think like transformations, so it's like the opposite way round when it's inside the bracket. So the centre is 4, 1. So that's point P. And our radius is going to be the square root of 17. This is effectively Pythagoras, like a squared plus b squared is c squared. To say that the distance is always the same no matter what point you pick, like how far away you are from the centre in terms of x and in terms of y. They're the two distances. And then the hypotenuse is going to be 17. So thinking of it like this, when you've got some circle, no matter which point you pick on the circle, you can think about that line there, and then to get the radius is just a right angle triangle. So using Pythagoras to get it out the other side. So yeah, radius, root 17. Find the points when C meets the coordinate axes for part B. We can use any of the equations that we've got to find that out. It's probably easier to use these ones, I think. So when it crosses the y-axis, x will be 0. So if we make x 0, what do we have? Y squared minus 2y 0. So we know that we're going to have y minus 2 times by y is 0. So our y coordinates will be either 2 or 0. So we're going to get the point 0, 2 and 0, 0. If we do a similar thing now, but y is instead of ax, we'll have an x squared minus 8x. So very similar steps as above, we're going to get 0 and 8 for this. So therefore, 8 and 0. And that 0 and 0 again, we don't need to count that twice. We've already counted that in our list. Counting it twice doesn't make a difference, so no need to write it down again. So the points A and B and Q, which is 8, 2, lie on C. The straight line AB is the diameter of the circle, so that PQ is perpendicular to AB. Okay, calculate the coordinates of A and B. So maybe let's sketch this. Let's draw a better circle than what I did up there. So let's have some circle. We know some things now then. So we know that it goes through, like if we draw an axis here, we can kind of just move that on and make sure that we get the points that we need. So we need to have this point, like 2 over there, 8 over there, and the origin. So you can see we can kind of move this across something like that. I know my 8 didn't come with me, but we can make that work as well. Like, so we know this is 8. We know, sorry, this is 8 and this is 2. So 8, 2 was the coordinates of Q. So actually our drawing is quite useful here because it's going to be exactly then above that 8 and across from the 2. So that's point Q. Our centre we knew was 1, 4. So we can actually see that we've got kind of like a weird rectangle where this is the diagonals and it's right in the middle. Whether that's useful, don't know. But it's always good to kind of spot these things just in case it is going to be useful. So Q is 8, 2. And we want to have the line from P to Q, P being the centre. So the line from here to here. And then we need AB to be perpendicular to that. So coming down at this sort of angle. Doesn't say which one's A and B, so I'll label that A, label that B, and label the centre one as P, as we should have done. So now, yeah, we've got a few ways we can do this. You can probably be a bit smart and think about kind of like the rotation of things. This will be 90 degrees and perpendicular. You can probably do some stuff with transformations and like swapping X and Y around. Most likely going to be easier though, if we just find the gradient of P and Q, like the line PQ, and then do the negative reciprocal, find that line and then plug the numbers in to figure out where A and B are. So the line PQ, what's the gradient? Well, similar to one before, we've gone from the point 4, 1 to 8, 2. So for every 4 steps to the right, we go up by 1. So that tells us the gradient is going to be a quarter. And think again, it's similar sort of idea then. This line, every step to the left we take, we're going to go down by a quarter. So every 4 steps left, we'll go down by 1, i.e. this is going to bring us back to the origin. So this blue line actually extends all the way through to the origin as a straight line. So the line PQ is actually just the line y is equal to a quarter of x. So using the negative reciprocal, we can see the line AB then, that's going to be y is equal to minus 4x plus some c value that we need to figure out. To do that, we can use the centre of the circle, point P, because we know it passes through that point. Also, I'm just looking at chat now. Hello, Abdul. Hello. If you have any questions about any of it, give me a shout. Sorry, I've got chat in front of me, but also I don't look up all the time to see what's going on. So hopefully that's made you happy. So how do we find point C? We can actually just take this equation and plug in the coordinates of P. Where is P? P was 0.14. So as we do that, we'll have 4 is equal to minus 4 plus C. So C is going to be 8 in this case. So the full line for AB is y is equal to 8 minus 4x. So now we've got this point, this line for AB. We've got the equation of the circle as well flying around. So we just wanted to think about the intersection of those two. Lots of ways we can do this, but probably easiest is just to take our 8 minus 4x, sub it into here. That will give us a quadratic in terms of x, which we can solve, and then take those x coordinates, plug them back in to get some y coordinates for them. So let's do that quickly. So what we're going to have, x minus 4 all squared, plus the y now is 8 minus 4x. So if we want one less than that, it's 7 4x. That all still gets squared, and it's all still equal to 17. So expanding the first bracket, x squared minus 8x, 16. And then for the second bracket, we'll have a 49. 7 times 4 is 28. Double that's 56. So we'll take away 56x, and then we'll add on 16x squared, and that will equal to 17. So if we collect all the like terms, how many x squareds have we got? 1 there, 16 there, gives us 17 altogether. How many x's? We've got 8 and a 56, so that's 64, all being negative. And for the numbers, if we take away 17, 16 takes 17 is minus 1. 49 minus 1 is going to give us 48, equal to 0. This doesn't look like it's going to have very nice solutions. In the exams, you're allowed to have calculators that solve quadratics, so I won't sit and just do a quadratic solution here. I will just go on my computer and see what answers we get, and then use them to find the y coordinates. So a good site is Wolfram Alpha. I use that quite a lot for any quick solutions you need to get for answers. So we've got x squared minus 64x minus the 48, all equal to 0. This gives us, not very nice numbers at all. So when we get numbers that are not very nice, so what we have here is 32 plus or minus 4 times the root of 115 all over 17. I'm always just going to double check that I haven't made a mistake. This number is not very nice. Often the questions are set up to have kind of satisfying answers or very simple answers. And then having this and then having to go through and find the y coordinate with that, not the end of the world. It's only times it by 4 and do 8 take away it. But still, generally, there's going to be much simpler numbers than what we've got here. So let's just double check we haven't made any mistakes anywhere. Did I expand everything correctly at the top? That should be x minus 4, 4 squared and a 1. So the 1 comes from down here. That all looks good. 16 and 1 makes it 17. That's all spot on. Then it makes it all called an axis. We didn't actually use these for anything in part C anyway. Points A and B and Q lie on C. That was that. The gradient was 1/4. Yeah, it goes across by 4, up by 1. So that's y equals that, because it goes back to 0. So the negative quarter with the C, plugging in the coordinates of 4 and 1. There's my mistake. So I've done 1 and 4 instead of 4 and 1. So let's scrap all of the last little bits we've done. The drawing we've got is still accurate, but just that little mistake can change everything going forward. So like we say, the y is going to be 1, and the 4 is 4. The x is 4. So we have minus 16 there, plus a c. So c is going to be 17. So y is equal to 17 minus 4x. So see, when you get answers that don't seem quite right, generally a sign that something has gone wrong along the way. So always just worth double checking that everything actually is correct. And if not, hopefully you can see your mistake as you look back. Nothing wrong with making mistakes, but it's good to be aware of like little triggers that can tell you that something is maybe wrong, and then just double checking all the little mistakes that you could have made along the way. So doing what we needed to do, we need this y equals 17 minus 4x and this circle equation to be like simultaneous. We want to solve them together. So let's think about, and here we've got y minus 1. So taking 1 away from here, you get 16 take away 4x. So let's plug that in instead. So altogether we'll have x minus 4 all squared plus, like we say, the y minus 1 is now 16 minus 4x all squared, and the whole thing equals 17. This looks very similar to each other. And in fact, this is kind of like negative 4 times as big as this one. So what I'm going to do for this 16 minus 4x, let's factorize out a minus 4. When that comes out the front with a square, that'll be 16. So we'll have 16 lots of x minus 4 all squared. And we've got the other x minus 4 all squared here is equal to 17. So how many on this side do we have altogether? Well, 1 and 16 makes 17. So this left-hand side is 17x minus 4 all squared. We can divide that then with this 17. So this ends up being x minus 4 squared is just equal to 1. So solving that, this is basically complete square form. So let's square root. We'll get x minus 4 is plus or minus 1, and then add the 4 over. So x is 4 plus or minus 1, which is equal to 3 and 5. These are much nicer answers than we got earlier. So yeah, good sign. If you're getting answers that are just disgusting, probably something's gone wrong, and just double check all these little number errors you could have made. So all I did was wrong was do 1, 4 instead of 4, 1. But obviously that then cascades through everything else and doesn't give you such nice solutions at the end. We do need the y coordinates as well. We can get them from either equation, the circles or the straight line. Straight line's easier to deal with. So for the point with 3 as the x coordinate, we need to do 4 times 3 is 12. 17 take 12 gives us a 5. And when we have 5 as the x coordinate, 4 times 5 is 20. 17 take 20, negative 3. So we should have those two solutions, 3, 5, and 5 minus 3. You often see, like, when you're doing stuff with circles, that the answers you get are very close to each other. You see, like, 3 and 5 just appearing twice in both of them. Not always the case, but that's a good sign that things have gone correctly. So yeah, we're done for that one. I will just shrink some of this up just to get some more space for question 4 below. How do we do that? We resize it, that's what we do. And hopefully, yeah, let's just do that. Push it up in the corner. Lovely, jubbly. So number 4, what have we got? A polynomial, f of x, is defined with the constants a, b, and c. So 2x cubed, ax squared, bx, and a c. And then we get some facts about it. So f of 2 and f of minus 1 are 0. And f of 1 is minus 14. We want to find a, b, and c, and then eventually sketch it and mark on where it crosses any axes. So to do this, these basically are going to give us 3 simultaneous equations. One when f2 is equal to 0, one f of minus 1 equals to 0, and one for the f of 1 equals to minus 14. So if we plug in the values of 2, minus 1, and 1 individually, and then set them equal to their corresponding numbers, that will give us those equations. So when we plug in the 2, we'll have 2 cubed is 8, times another 2 is 16. 2 squared is 4, so we'll have 4 lots of a. 2 times b, 2 times b. And then plus a c, and that will all equal 0. So, well, do the other ones. We need the minus 1 in there. Minus 1's quite nice at polynomials. You can basically just alternate plus and minus between the coefficients. Here, the leading power is 3. So minus 1 to the power 3 is minus 1. So we're going to start with negative 2, add a, take b, add c. And that will all equal 0. Again, that 0, both those zeros coming from this 0 here. Exactly the same idea now with this 1 and 14. And again, 1's very nice with polynomials. Just add up all the coefficients. So we'll have 2 plus a plus b plus c equals minus 14. So now what we have is a set of simultaneous equations with 3 different equations in there. If you do further maths, you can probably go through and use some matrix stuff to solve this. But I'm going to try and not use any further maths knowledge to solve this, so that people that are just doing single set maths can follow this as well. So how do we want to do this? There's kind of a lot of options that we can do. I think one that might be nice is like to eliminate c from all of them if we can, because that's just a plus c everywhere else. And then we're just dealing with 2 equations, just a and b, which we can solve using stuff from like GCSE level. So let's just pick 2 of the equations. Let's go to the top 2, and we're going to subtract 1 from the other one. So doing that, I'm going to have 16 take away negative 2 gives me an 18. 4a take away a is going to give me 3a. 2b take away b gives me a 3b. And c take away c gives me a 0. And 0 take away 0 also gives me a 0. So that's now one equation with just a and b in there. We need to do the same with a different pair of the original 3. So we've done this top 2. Let's have a go at doing the bottom 2, because you can see they're quite similar anyway. So actually if we subtract them again, what are we going to get? Actually even easier. We could have done that first step. So look what's going to happen. Minus 2 take 2, minus 4. A take away a is 0, so plus 0. Minus b take away b, minus 2b. And then 0 take away negative 14 is going to be positive 14. Same thing happened with the c's as the a's. They're both positive, so they just cancelled out straight away. So this one, we can actually just solve for b immediately. Let's add the b over, and we'll take away this one. So we'll have that 2b is equal to minus 18. So b should be negative 9. Now then, we can go back through and use this 9 to figure out the values of A and B. This equation already doesn't involve C, so by plugging in the value for B, we will get the value for A straight away. So doing that, we'll have 18 plus 3A plus 3 times negative 9 is actually minus 27, and that will equal 0. Adding everything over to the other side, 3A will be 27 take 18, which is 9. So A is going to be 3. Let's just circle both of these so it's easier to see backwards. And now take any of the equations above, plug in the values for A and B, and that should give us the value for C. So on this one, we'll have 2 plus the A, which was 3, plus the B, which was negative 9. So take away a 9, plus a C is equal to minus 14. Rearranging that for C, this is 5, take away 9 is minus 4. Adding that over, it's going to give us 4 take away 14, or minus 10 altogether. So there are our values for A, B, and C. All quite nice, simple numbers, which is a good sign everything's going well. For part B then, we need to sketch this graph. So to sketch it, we need to factorize it as well. So let's actually just write out the full, the full quadratic that we have, quadratic cubic even that we have. So 2x cubed, A was 3, so we'll add 3x squared, B is minus 9, so minus 9x, and the C is minus 10. We can use this though. So because these were equal to 0, 2 and minus 1 must be roots of our equation. So doing that, we're going to have the kind of 3 brackets. We already know 2 of them, where we're going to have the 2 will give us x minus 2, and the minus 1 will give us x plus 1. So we can get the remainder over here by just thinking about, like, where does this 2x cubed come from? It must come from x times this, because they're the only ones to give us enough of a power of x, basically. So you've got x squared, x cubed come from this bit. So, and then the coefficients, 1, 1, what number do we need to times by to get to 2? Has to be 2. So this should be a 2x. We can do exactly the same process with the constant term. It must come from all 3 constants times together. Minus 2 and a 1 makes minus 2. I need a minus 10. So this should be plus 5. So now if we go to sketch it, we can see that we have positive x cubed. So it's going to be a smiley face graph. And actually it's a bit easier to sketch it by just drawing the quadratic first and then trying to see where the points need to be. So we need 1 at minus 1, 1 at 2, and 1 at minus 5 over 2. So 2 of them should be negative and 1 of them should be positive. So if we just draw a line across like that, and then something going down, just be a little bit careful about where we draw this y-axis. This should be point 2, and we need to make sure that we don't know exactly if it's on the curve here. It actually hasn't given us any hasn't asked us anything about the turning point or anything like that. So I think if you draw the line this side or this side, both of them should get you full marks because you're still getting all the correct stuff in there. So if we do that, let's just draw it this side here and then mark everything on. So this should be the point 2. This is the point minus 1. This is the point minus 5 over 2. And then we've also got the y-intercept, which we can get just from the original quadratic of minus 10. It's a bit of a long-winded question. Like I say, there's probably some easier ways with matrices to actually go and solve these sort of questions. But if you don't do further maths, you probably haven't learned that sort of knowledge. But you can always do it just by slowly eliminating them. Basically think of them as pairs, and then keep doing pairs until you slowly eliminate. So this pair eliminates C from both. This pair eliminates C from both. That gives you 2 involving just A and B. And then just work simultaneously with those, eliminate either A or B from those ones as well. So hopefully that's all making sense. Let's have a look at question number 5. So our first trig stuff. Give me one sec. So what have we got? We need to solve it in the given range. 5 cos 2x plus sine 2x over 3 sine 2x is equal to 7 in the range from minus 90 to positive 90. So first things first, fractions. They're our friends normally, but in these sort of questions, we want to get rid of them. Whenever we solve in equations, try and get rid of the fractions as quick as possible. So we're going to have 5 cos of 2x, if I could write the word cos, plus sine of 2x is all equal to 7 times 3 sine 2x. So that's 21 sine 2x. So this is going quite good. We've got 1 on this side, 21 on that side. So actually what we have is 20 on this side altogether. Still equal to the 5 cos. Let's divide by a 5. So a single cos of 2x is now 4 times by sine of 2x. And let's divide by a cos. We're going to do that so we get tan, and we'll divide by the 4 as well. So what we get for the final kind of equation to solve, tan of 2x is equal to a quarter. Now, so this is down to kind of the simple point. You'd have learnt this like one of the first things in trig stuff in A-level. So when you sound like 16, the first stuff you'll be doing. To solve this, I want to first of all manipulate my domain to match my operand in the tan function. So as x goes from minus 90 to positive 90, 2x will go from minus 180 all the way up to positive 180. So if we just go and draw the tan graph now, in that range, in that domain, so starting at minus 180, and all the way up to positive 180. Probably easier to draw the middle one and work out. So there's the middle one. This would be 90 and 90, like minus 90, positive 90. And then we just need the other little parts of both of these. So going up there and coming down from the bottom up to this point. Where is the quarter we're trying to find? Somewhere up here. It might be higher, it might be lower. Doesn't really matter. It just tells us that we have 2 solutions to find. So when we, in our calculator, find the inverse tan of a quarter, this will be the principal value. That's for tan, always between minus 90 and positive 90. So if we do that, what number do we get? Inverse tan of positive 1 on 4. We get it's 14. I won't worry about decimals, so it's 14 point something, but yeah, 14 will do. So this has exponents of 14. How far away are these two? Well, the tan graph is exactly 180 wide. So this, you just need to take away 180 from the 14 we found. So the final answers should be that 2x is the 14, and 14 take 180. So minus 166. So a single x will be 7, and half of this, which is 83, or minus 83. So I think that's a bit easier. Like changing the domain to match, that should say 2x in there, sorry about that. Yeah, changing the domain to match the operand that you have for your trig function, so that then when you actually go to draw the graph, you can just draw it normally. And all the stuff about like taking 180, you don't have to think about like, oh, for tan 2x, it's going twice as fast, so it's going to be 90 instead. Because it can get a bit more confusing when you've got something like 2x plus 4 or something along those lines. It makes it a little bit more tricky to deal with. So yeah, that's that one. Hopefully a nice easy 6 marks compared to what it could be. Looks a bit more horrendous. But if you just kind of attack the bits that look the worst, like I don't want the fraction, let's get rid of it. And then you kind of spot things like, oh look, there's just lots of sine 2x's, which you can deal with together. So try not to think of the whole thing in one go, but there's little bits of it, and all of a sudden you can kind of see exactly what's happening later on. So question 6. We've got a cubic equation, has real roots x1, x2, and x3. Use transformation arguments to find a simplified form, another cubic equation whose roots are just one more than the one above. So thinking about this is a transformation to the right, like a translation to the right by 1. So how do we represent that? It would normally be f of x minus 1. So that's what we want to do here. Every x in here, we're just going to replace with minus 1 and expand all the brackets. So we'll have x minus 1 all cubed, minus 4 lots of x minus 1, and then a plus of 1, all equal to 0 still. Let's expand all of these brackets. When we do this, it's like binomial expansion. So we're going to get an x cubed, we're going to get an x squared, we'll get an x, and we'll get a 1. So thinking about the powers now, like we've gone down in the powers of x. 1 doesn't change power if we increase it. So all we need is the coefficients, which come from Pascal's triangle. So it's going to be 1, 3, 3, 1. So 1, 3, 3, and 1. And then the negative is going to cause us to alternate. So starting off, we're going to have a positive, then a negative, then a positive, then a negative. The minus 4 and x minus 1 will make minus 4x and a positive 4. And again, we still have that positive 1 at the end, and we're all equal 0. So let's collect all the like terms. How many x cubes have we got? Just this one. How many x squareds? Again, just this one. There's none coming from this part at all, so you can kind of like discount it when you're thinking about the higher powers. So that's minus 3x squared. How many x's? We've got 3 there, and minus 4 over there. So that's minus 1 altogether. And then how many just constants? Well, I've got minus 1 and a positive 1. They cancel out. So I'm just left with this, other way around. These ones cancel. I'm just left with this positive 4 over there. So that should be the new cubic equation with these different roots compared to the one that we were told about up here. Notice we never need to define the roots. That's not part of the problem. You probably could, but I think looking at it, they're not going to be very nice numbers, especially when you've got a 1 on the end. Generally, like, all of the roots that you find will be factors of that number or some fraction of those factors. Thinking about like where we had this one earlier on, where was it? Yeah, this one we factorized earlier, the 10. All of the factors 2, 1, 5 are all factors of 10. So where we have this this 1 on the end, not going to be so easy to find the factors of that. So lovely. Only 4 marks for that. Actually, not too much work to do to actually solve the question. What have we got next? So it's number 7. A curve has this equation. Again, we've got more cubics, lots of cubics in this one. You don't normally see so many cubics lying around. Point P lies on C where x is 1. Find an equation to the tangent. So we need 2 things. We need the y coordinate. So let's get that quickly. If we plug in the value of minus 1, what can we minus with minus 1? Like I said earlier, you're going to alternate positive and negative with the coefficients. Leading power is cubed. Minus 1 cubed is negative. So it's going to be minus 4, and then positive 7, minus 1, positive 11. So let's add these as we go. That's 3, that's 2, that's going to be 13. The next thing we need to do is differentiate. So find dy dx. For the 4x cubed, bring the cube down to make a 12, like 4 times 3. Drop the power to squared, 12x squared. The 7 times the 2 gives us a 14. Dropping that power, so it's a single x. And then for the single x by itself, we get just a plus 1. So let's go and find the actual gradient of this line then. We're going to have to plug in the value of minus 1 into our polynomial, into our like derivative for the gradient function, basically. Same thing happens with this. It's still a polynomial, so we're going to alternate between powers. The leading power is squared. Minus 1 squared is positive, so it's going to be 12 minus 14 plus 1. So 12 plus 1 is 13, minus the 14 will give us negative 1 altogether. So we've got gradient negative 1 and the point minus 1, 13. So we can do a few things to find the full equation for it. I think this is meaning that every step to the right we take 1 step down. We need to take 1 step to get back to the y-axis. So we're going to take 1 step to the right and then just the 1 step down. So it should cross at 0, 12. So therefore, the full equation should be y is equal to minus 1x, so just minus x, plus 12. You could write 12 minus x, both will get you the full marks. Don't worry about that much of it. What we've got to do for part B, the tangent to C at P meets C again at the point Q. Determine the x coordinate. Okay, so in this sort of case, again, it's intersecting lines. We've got a tangent and we've got a cubic. I don't know exactly where this cubic's going to be happening or where exactly the tangent's going to be, but effectively, imagine the tangent was happening here. It's going to come through and just stab the line again at this point. So we want to solve them as simultaneous equations. So doing that, let's just set them equal to each other. We'll have 4x cubed plus the x plus the 11 is equal to 12 minus x. I have wrote it this way around instead of the minus x plus 12, but all is good. Bring it all to one side, make it equal to 0. So x cubed don't change, x squared, we'll add an x to get a 2x, and take a 12 to get minus 1 equal to 0. So now, earlier on we needed to factorise one, and we had some roots already, made it much easier. But what we should know is that this is actually a repeated root at the tangent. So minus 1 should be a solution twice. So i.e. we're going to have x plus 1 squared. I will write it out as x plus 1 again, And then the other bracket, we can actually be a bit sneaky. So same idea. Where does this 4x cubed come from? It's going to be this x, and the x in there. We need to make a 4. This has got 1 and a 1. Times them together, you're still at 1. So we need a 4 to get all the way up there. So 4x in there. And then same idea on the end. Positive 1 gives us positive 1. We need a negative 1. So it must be negative 1 on there. So that tells us the other root should be 1/4, which comes from just solving that equal to 0. Lovely. So yeah, not too bad for that one. Looks like it's going to be a bit worse, but knowing the fact that the tangent is a solution to this, we're not finding the root to the equation of the quadratic, the cubic even. We're just finding where the two intersect. And it intersected here like a repeated root, so therefore it appears twice. Let's keep going. Number 8. So we have some quadratic equation. We want to find the above equation as a product of two linear factors. Detailed method must be shown in this question. So I think that thing is just telling us, like, don't just use your calculator, solve the quadratic, and then think, like, if you get like 5 and 2, you can just be like x minus 5, x minus 2, and then we need a 12 at the front. So we can't be doing that sort of stuff. We have to actually do some sort of method. So I think the easiest thing is to look for factors of this number. So I think by looking at it, it's not even, it's not a multiple of 3, not a multiple of 5. I think it's a multiple of 7. Let me just check on the calculator. Yes, it's 23 times 7. Both of those are prime numbers. So I'm going to make the assumption that the linear factors that they want are going to have whole numbers in them. They're not going to have square roots and things. We can make that assumption, and then if it turns out we're wrong, we just try it again in a more complicated way. But this, if it works, it's going to be a little bit of a shortcut. If it doesn't work, no harm done. We just try again a different way. So 723, they're going to go in to our brackets. We need to make minus 61. So one will be positive, one will be negative. We don't know which one's which yet. And what we need to be looking at now is the factors of 12. So for 12, we can have 1 and 12. We can have 2 and 6. We can have 3 and 4. Somehow, we need to do a combination. So for example, the 23 and the 4, and the 7 and the 3, and have their difference be 4. So thinking about that, it's kind of obvious that we need the bigger number to go with the 7. If we did like 4 times 23, that's already so much further away than the 3 times the 7. It's never going to have a difference of 4. So let's try having 7 and 4 is 28. That's 23 and 3 is 69. So much, much too far away. If we do 2 and 23, that makes 46. And the 7 and the 6 makes 42. So that's 4 difference from each other. So that's a very good sign. So thinking about that, that tells us then that the 6 had to go with a 7. So it doesn't go here because it needs to times by the 7. So it's going to go in this bracket, and therefore the 2x will go in this one. And then just double checking the positive, negative sort of stuff. We need positive 4. So we need to make sure that the 2 and the 23, which give us 46, is bigger than the 6 and the 7, which give us 42. So we need a positive 23 to be bigger, and then taking away the smaller number of the 42. So that should be our two linear factors we have for f of x. There are other ways to do this. You could probably trial and error, but trying to guess like 7 halves and negative 23 over 6 is not going to be so easy. And you could do the AC method where we do 12 times 161. That's quite a big number. And then looking for the factors of 12 and 161, not going to be so nice. Wouldn't be the end of the world because we have a calculator. If we know that's 23 and 7, this is going to be 2, 2 and 3. So you can just kind of like do lots of the different powers of the factors and see if it's going to work. But I think this method is a shortcut if it works. So with the assumption that all our numbers are going to be whole numbers, everything should work like that. And actually the other one assumes that anyway. But it's obviously a little bit of a tricky thing to kind of mess this about to try and make it work. Hopefully that all makes sense. We'll keep going down, see what's going on with the other ones. So show that if x is numerically small, that this thing, 2 plus x minus x squared to the power of 5, is roughly equal to some cubic without x squared in it. So to do this, like, this is about an expansion. This is a trinomial. You don't learn about trinomial expansion, but you do learn about binomial expansion, where you have a constant and some power of x. So we're going to do it in a slightly different way, where we're going to take that bracket, but write it as 2 plus a small bracket of x minus x squared. And then we're going to deal, like when we're doing the binomial expansion, what we're going to have is basically that this bracket is acting like the x or the ax that you normally see. So if we were to expand this out, what would we get? We'll get the 2 to the power of 5. We're going to have another bit then with a 2 to the power of 4 and an x minus x squared and a 5 choose 1. 5 choose 1 is 5. Then we're also going to get a 2 to the power of 3. We're going to get x minus x squared all squared and a 5 choose 2. If you think about Pascal's triangle, that row goes 1, 5, 10, and then reverse 10, 5, and 1. So this should have a 10 on the front as well. Think about this, we only need to go to x cubed. So do we need the next term? Yes, because that's going to have this x cubed on it. So we do need that term. Let me just slide everything over. So adding it on, another 10, a 2 squared, and then x minus x cubed. So x minus x squared, all cubed. Now then, we just want to expand all of these brackets and collect all the like terms. So for the first one, 2 to the power of 5, that is 32. In here, no expansion needed, because like it's just, well, a little bit of expansion needed, but no power on it, which is nice. This is 16, this is 5, altogether they make 80. So we're going to have plus 80x, take away 80x squared. This is 2 cubed, which is 8. Times by 10 is 80 again. So if we just write that there a little bit, we've got 80. And this is going to expand with an x squared and then a negative x cubed, 2 of them, and a positive x to the 6. No, x to the 4 even. So we don't need to worry about the x to the 4. We do need up to x cubed, but we don't need x to the 4 at all. So doing that, we get the 80 times the x squared. We'll get, like I said, a minus 2x cubed in there times 80. So minus 160 x cubed. And then, yeah, we don't need to worry about the 4 bit because we don't need to go up as high as power of 4. Similar thing's going to happen here. Most of the expansion of this bracket is going to be at least a cube. In fact, there's only one bit that's going to be a cube, and that is just when you have all 3 of the x's by itself, giving you exactly x cubed. And in that case, we'll have 2 squared is 4, times by 10 is 40. So we should have 40 x cubed there in the end. And now, just a case of collecting all the like terms. We'll see some bits will cancel out. We have a negative x, 80x squared, positive 80x squared, so they cancel out straight away. And we're left with just a 32, just an 80x. And then if we think about these numbers, 40, take away 160, is negative 120x cubed. This should have like plus or higher powers. And again, this should have plus higher powers, but we don't really care about them. So like we said, we're doing just an approximation. So we only wanted up to x4, exactly what they've given us in this kind of desired form, basically. So yeah, not too bad for 6 marks. I suppose it's just spotting that you can do a trinomial expansion in kind of a makeshift binomial form. It's still exactly the same. There's no weirdness has gone on. You just need this thing then to be, like the modulus of this to be less than 1. Didn't ask about that in this case, but in case it does in the future, that's what you need for that. Number 10 then. So straight away, as soon as you see this, it's going to be some like first principles, differentiation. You very rarely see anything like that in any other kind of context. So let's think, f of 2 is easier, so let's actually start with f of 2. We're just going to sub that in. So subbing in the value for 2. 2 to the power of 4 is 16. 4 times 2 is 8. 16 take 8 is 8. And now when we go and do the 2 plus the h, we're going to need to do 2 plus h all to the power of 4. So another binomial expansion. We're going to get 2 to the 4, and then 2 to the 3, and then 2 squared, and then 2 to the 1, and then 2 to the none, which I won't bother drawing in there. The x is going to be a h. So we need to have h to the 0, then h1, h squared, h cubed, and h to the 4. and then the Pascal's triangle. So it's going to go 1, 4, 6, 4. So doing that, we have 1, and then plus the 4 times this stuff, plus 6 times this stuff, plus 4 times this stuff, and plus 1 times the h to the 4. Let's just simplify all those little bits. 2 to the 4 is 16. 2 to the 3, 2 cubed, is 8. Times 4 is 32. So 32, lots of h. 2 squared is 4. Times 6 is 24. So you have 24 h squared. And then here, 4 times 2 is 8. So 8h cubed. And then just plus the h4. Remembering this is just for f of 2 plus h. We need the difference of these two. So this entire thing we've just found, but take away the 8. The only thing that's going to change then, this 16 will transform into 8. So 8 plus 32h plus 24h squared plus 8h cubed plus the h to the 4 all popping out. I'll just move that slightly so we can see all of it. Nice. So that's part A, 4 marks for that. You can see basically 4 marks for doing the binomial expansion. That's kind of what they're giving you the marks there for. So now we want to use the formal definition of the derivative as a limit to show that the derivative of f at 2 is equal to 28. Well, thinking about the actual definition, you would have the limit as h tends to 0 of f of x plus h, take away f of x. If we just think of the x as being 2 straight away, it is 2 plus h, take away the f of 2. Exactly the thing we just found, all divided by h. So we effectively want to take what we found there and sub in. Why is this not looking like it should be working correctly? What's gone wrong? Oh, I've missed off the 4x. So let's go back a step. We need to just go on this one. Down here is do 4 times 2 plus h. So 4 times 2 is 8. So take away an 8, and then take away 4h as well. So this makes more sense, yeah. So the h disappears, which is quite good. Makes it a bit easier going forward. So this, again, how did I know I was wrong? I know that I'm going to divide by h. So I should have everything in here should be a multiple of h or some power of h. Because we had this 8 here, it was going to be 8 over h. We cannot plug the 0 in as h. It's going to break the calculator, so not allowed. So that's how I knew something was wrong. And all we need to do is go back up and see now the 16 minus the 8 minus this 8 will give us a big fat 0 instead. Also, the minus 4h is going to change this 32 into a 28, which you can see is going to be kind of the answer that we have from, like the show that part of the answer. We already know that that 28 is useful. So doing the actual limit now, like we say, we've got this entire thing, but divide by h. So we need the limit of what we've just found as it tends to 0. And what we just found was then 28 plus 24h plus 8h plus h cubed. And then, yeah, when we plug in 0 as h, which we're now allowed to do because we're not going to break the calculator anyway, all of these bits become 0. We're left with just single 28 on the other side. So yeah, not too bad of a question. Like I say, these little triggers you can know about to know if you're wrong. It's like what's going to happen with this is always going to do that division of h. So we can never have a h on the bottom left over. So because we had that 8 in here, dividing it by h would have broken our calculator. We cannot plug the 0 into there. Gives us a sign that something is wrong. And just go back a few steps, see what was wrong and try and figure it out again. Number 11 then. Find, without the use of any calculating aid, the solution of this equation. So they're all powers of 2, first of all. I'm not going to worry about this 64. I'm not going to make that into like 2 to the power of 6. I'm going to leave it as it is. But the actual base 64, we will change that. So let's think what we have. I've got 2 to the minus 1 times by 4, which is 2 squared, all to the power of 2x. And then 64, yeah, it's 2 to the 6, all to the power of 64 still. What we could do is, yeah, we could make that into, again, 2 to the power of 6, but I don't think we need to bother doing that. I think we just leave it as it is. Going forward then, when we have powers like this, kind of like you've got a power inside a bracket and then it's all to another power, you just times them together. So we can write this again. This is 2 to the minus 1 times by 2 to the 4x, and that's equal to 2 to the 6 times 64. 6 times 64 is 384. And the last few steps, this we can either combine it together with the 4x, or you could like effectively times by 2 and bring it to this side and make that into then 385. Both ways work out to be the same equation of 4x minus 1 is equal to 384. So 4x equals 385, x is equal to 385 divided by the 4. So again, hopefully not too bad of a question there. It's just a case of like not messing around with the power, I think, here. Makes it a little bit easier to work with. So let's keep going. We're nearly finished now. I think there's 15 altogether. Yeah, it's the last page. 13 altogether. So yeah, we're nearly done already. So what have we got now? We have some closed cylindrical can, radius r, height h. The volume of the can is 330. So the surface area is given by this lovely looking thing. So volume of a cylinder, we need the cross-sectional surface area, pi r squared, times by the height or the length, which is just h in this case. And like we say, that we know that's 330. So that gives us one equation. We can then get the surface area equation as well. Doing that, we need the two circles, top and bottom. So that's going to be pi r squared, but times by 2. And then imagine imagine this is a tin of beans. If you take the label off a tin of beans, what shape is that label? It's a rectangle. So we've got the height here, and the other side of the rectangle will be the circumference of this circle. So it's going to be, we need to add on 2 pi r for that circumference times by the h. This then, we want to kind of combine these two together. Looking at our kind of goal expression at the end, we have no h's. So we want to take one expression, rearrange it for h, and plug it into the other one. We're looking for the area, and we have a value for the volume. So we start with the value one, the one that we have a value for, the volume in this case. So h is 330 divided by pi r squared. So now let's sub that into this bit. This is still the same. When you can see that's good, that's exactly the answer over here. We still have the 2 pi r squared. And then the h, when we sub that in, we're going to sub this in instead. So 2 times 330 is 660. We've got a pi on the bottom and a pi over there. So they're going to cancel out. And then we've got an r on the top here and an r on the bottom there. So they're going to cancel out as well. And that's everything then all done. In the exam, I'd probably do a step in between just to show that you understand exactly what's going on. So like pi r squared here plus 2 pi r, pi r times by that 330 over pi r squared. Both ways give you the same thing, but yeah, just to make sure that they can see that you followed all the steps and not just kind of done some stuff and then written the answer down, we'd have this intermediate step as well. So that's part A done. Part B, find the value for r for which r is stationary, A is stationary, sorry. So we need to differentiate. This, we can write the 660 over r as 660 r to the minus 1. So if we now go and find dA, dr, 2 pi r squared will give us 4 pi r, which is a formula that you may be familiar from something else. The 660 then, we're going to make minus 660, and the r is going to drop power. So instead of minus 1, it's going to be minus 2. We want to find when this is stationary, so this needs to equal 0. This doesn't look very nice as it is there. It's probably easier to write it as 4 pi r, take away 660 over r squared is equal to 0. And then trying to solve this is a little bit nicer than what it was there, because we can just set them equal to each other, like adding the 660 stuff to the other side. And then effectively it times in by the r squared to make r cubed on this side. I will then divide by 4. 330 is half of that, and then half again is 165. I will double check my maths on the calculator. Yeah, 165. So pi r cubed is 165. R cubed is 165 over pi. So r is going to be 165 over pi, all cube rooted to the power of 1/3. That should be for part B. Part C then, we want to justify that that is a minimum. So to do that, what we need to do is differentiate again. So taking the expression that we found over here and differentiating for the second derivative. So d2a dr squared. The 4 pi r will become 4 pi. We're going to have the minus 2 come down to make a positive 2 times 660. 660 times 2 is 1,320. Okay, we'll double check that. 660 times 2, yeah, 1320. And drop the power of r, so r to the minus 3. What we can see then, this is positive. When we do it cubed, it's going to stay positive. If we reciprocate it, it's going to stay positive. Timesing it by this number, it's going to stay positive. And adding something to it, it's going to stay positive. So we can plug in the number we wanted to, but I think you can do that idea. This is how I would do it. Like r is positive, which tells us that r cubed is positive. So that tells us that r to the minus 3 is positive, which tells us that 1320, r to the minus 3 is positive, which tells us, and actually strictly positive cannot be, yeah, that's already strictly positive. And then if we add on 4 pi, we are again still positive. We'll move this all over a little bit, give me some more space. Which then is the entire thing. So we've shown that the second derivative is positive for our value of r. And actually it's going to be positive for any positive value of r that we found. A negative, it's only going to be negative for a sum of them. It's going to depend on like exactly what value we get to make sure that this kind of works out to be negative. But any single positive value for r is going to be a minimum by definition. And now then, calculate that value of a. Not very nice, but we need to sub this into our original expression that we had up here. So a is going to be equal to 2 pi and then r squared. So the 165 over pi squared, when you've got a cube root, it's going to make the power 2 over 3. I'll make that 3 a little bit nicer. And then 660 over r. Instead of writing it over r, I'm just going to flip it upside down. So 660 pi over 160, 165 even, all to the power of 1/3. We should probably expand this a little bit. It's not going to be a very nice expansion. May well be that we just put it in the calculator as the proper way to do it, but I will show you some ways that we can kind of do it without it. So let's first just factorize. You can see that we have like 2. This is a factor of 2, so we can take that out the front. And the big bracket as well. You've got like 2 over 3 here and 1 over 3. So we can take a factor of like 1 over 3 as the power out at the front. And then what are we left with? For this term, we needed a pi. And we also need the bracket, the 165 over pi, all cube rooted. And then we're going to add on, the only thing missing from here is 330. Doing some more expansion then, this bracket stays the same at the front. In here, we can do some stuff. We're going to have 165 cube rooted. Pi over pi cube rooted is pi to the 2/3. And then we're going to have just that plus 330 on the end. There are probably ways that we could do this nicer. Maybe they just want you to stick it in the calculator. Maybe they don't want this. It's worth probably checking, like when I'm revising, I would then check the mark scheme to see exactly what they wanted from this. In the exam, I'd probably do both. I'd write down this thing and then also whack it in my calculator and see what number it gives us. Whether this is nicer than this one is kind of subjective. It's written in a more factorized form, whereas this is in like an addition form. So it's like, do you need to divide with it next or times with it next? If so, that way is probably nicer. If you're just going to add and subtract it, it's probably better to leave it in this form. Both should be equivalent. Like I said, I would whack it in the calculator in the exam and see exactly what number we do get out from that. I will do that for you now quickly. So it's probably easier to do the first one, I think. We'll have 2 pi, 165 over pi, all to the power of 2/3. I've typed that in wrong, hold on. So 2 pi, open bracket, 165 over pi, close bracket, power, 2/3. Very fiddly to put this in. So in the exam, I would double do it as well, just to make sure you get the same answer. And then we've got 660 pi over 165, all to the power of 1/3. We get a number 264. Always double check as well. Does that seem kind of realistic? We had a volume of 330. This is just a can, like a can of Coke you'd get in a shop, something like that. So this seems about right. I don't know off the top of my head what the area of a can of Coke should be, but this does seem about the right sort of number that we should get. Not a huge area, but not obviously a tiny minuscule one either. So good, that's number 12 all done. Let me again just move this out the way a little bit so we've got some more space for the question below. Shrink that up, shove it up here. Is that in? Yeah, that's all in. So is this the last question? I think it is. Yeah, last question. We have some simultaneous equations for log stuff. So what we want to do is, this is base 2 and this is base 3. So they're not really nice to combine together. It's probably easier to turn them back into like exponential questions and then equations, and then try and solve them simultaneously there. So this, we have the logs on either side, and we have something that isn't involving logs. So always bring all the logs to one side, combine them, and then get rid of the logs. So doing that, we're going to have log 2 of the y minus 1, take away log 2 of x, and that is all equal to 1. And that then is going to give us, on the left-hand side, we can combine those together. We'll have the log, again base 2, of y minus 1 divided by x is equal to 1. And those log laws then, if I just going to try and make some more space over here, that's not going to fit. Y minus 1 over x is equal to 2 to the power of 1, i.e. just 2. So y minus 1 is 2x, or we can say that y is equal to 2x plus 1. Similar process for the one with the base 3. Looking at this though, it's going to have the 2 on the front, so it's going to make it squared. But let's first bring them all over. We'll have 2 log 3 of y is equal, take away log base 3 of x. We'll put brackets there too. All equal to 2. And like I say, yeah, we need to do this 2 before we do the subtraction. So it's going to give us y squared over x. Not y over x all squared, but you square just the y and then divide by the x. That's still in the base log 3, we're equal to 2. So what we can say, y squared over x is equal to 3 squared, i.e. 9. And again, just getting rid of the fractions, y squared is equal to 9x. So now we have the two equations, and they're in much easier forms to deal with. So to do that, we're just going to sub one into the other one. So to sub in the top one into this bottom one here, we'll have 2x plus 1 all squared is equal to 9x. Expanding that bracket on the left, 4x squared plus 4x plus 1 equals 9x. And I will just move this all to the left a little bit so I've got some more space to work with. Move that all there. Move you up here. Bringing everything to one side, we'll have 4x squared minus 5x plus a 1 equals a 0. And this then, just a quadratic to solve. So like I say, in the A-level stuff, you should have a calculator that solves this for you. We can just go through, hopefully, and see what numbers we need. So the 1 is here, so it's going to have 2 1s at the end, most likely. And we need numbers to time together to make 4, but then add up to make 5. So it's got to be 4 and 1. 4x and a single x. And we need a minus 5. So actually, both of these are going to be negative in there. So final solutions should be a quarter from the left bracket and 1 from the right bracket. And that should be then, yeah, the final answers for this whole paper. I think that's all done. I don't think I've made any mistakes. All the answers seem quite nice. I haven't looked at the answers or anything beforehand, so I'm not entirely sure if that is all correct, but it looks, most of the answers seem quite nice. When you get answers that are all whole numbers or nice fractions like that, especially like you think how complicated some of the processes have been, it would be a good big coincidence if you got whole numbers out without like making, like you wouldn't, if you made a mistake, you wouldn't get whole numbers out. The fact we've got whole numbers out probably means that we've not made a mistake anywhere along the line. So yeah, I think it's probably worth us actually getting the answers up, and then we'll have a little look through it. So what I'll do is I'll get this up. That's the paper. Where's the answers? Solutions. And I will split this so we can see. Is it back? Sorry, it all died, which is not good. Is it back? It might be back. We're very nearly at the end as well. Let me refresh my thing in front of me. Sorry about that if it's died, that's not useful. Give me 2 secs just to make sure it's all back up and running. Yeah, looks like it's back now. So yeah, let's just double check quickly. We can see this is question 1 here. We've got the 9, 8, we got the 6, so that's all good. Question 2, what answer did we get? 9 halves. Yep, lovely, that's all good as well. Let's have a look at number 3 on the next page. What answer did we get? 3, 5. It's up here, isn't it? 3, 5, and 5 minus 3. Later on. The first bit as well. Like, generally, if you've got the last bit right, you've got everything else right as well. But yeah, 17, the 4 and the 1, wherever it is. Yeah, that's good. Was it 3? 3, 5, and 5 minus 3. Yeah, lovely. Like I say, yeah, generally, if you've got the last bit right, you've got everything else right along the way. What numbers do we get for question 4? A was 3, B was minus 9, and C is minus 10. Lovely. So we get the roots of 2, minus 1, and minus 5 over 2. So that's all looking good as well. Question 5, what did we get? 7 and minus 83. I did round it, but yeah, 7 and minus 83. Lovely, jubbly. Number 6. What do we get for number 6? I said that the answers were, so we should have x cubed minus 3x squared minus x plus a 4. Yep, that all looks good to me. Excuse me. Number 7. P minus 113. Yep. X plus y equals 12. Yeah, same thing. And then 1/4 at the very end. Yeah, lovely. Number 8. 6x and 2x minus 7. Yep. Question number 9. 32 plus 80x minus 120x cubed. So that all looks good as well. Question 10. What do we have? Question 10 will show that. So, yep, we got that all good. And 11. 96.25. Yeah, 385 over 4. Lovely jubbly. Over here, that was a show that for the first bit. Find the value that they wanted. 165 over pi. That's what we have at R cubed, and then they've just cube rooted it. Yeah, so that's all good. Everything looks nice there. So yeah, this was the one. Did they? Yeah, they just plugged in the things. They didn't bother doing any like weird expansion that I was doing, wherever that was. Yeah, all this stuff up here. But you see, we did get 264. So exactly spot on. No, nothing to complain about there. Last question then. We should have got 1/4 and 1. Oh, I didn't find the y. I didn't find the y values. Okay, so we lose a single mark at the very end of it. But we can see, yeah, just going back, plugging those x coordinates back into y, we will get those bits. I will write that in there for completeness. So we get 1/4. I can see it's 3 now, but we can get that quite easily from seeing, where is it, 2x plus 1. So yeah, doubling that would give us a half, adding 1 is 1.5. So it gives us 3 over 2. And then for the other one, we had a 1. Doubling that gives us 2, adding 1 gives us 3. So yeah, apart from that little, just forgetting the y values at the very end there, everything is all spot on. Happy days. So yeah, this is paper A of this IYGB stuff. There are loads of them. Where I got this from, if we look on the one on the left, if you're going to move. There's loads. Is that a whole alphabet? Yeah, it goes always to Z. So I think I will just keep doing these. Like I said, these are for all my students that I'm tutoring anyway. So I will send them all to them eventually. But if I can go through and do them here, someone in the future may well watch this and find it useful to see like the whole thing worked out. So anyway, watching, thank you very much. If you have any questions, give me a shout. If not, yeah, good luck. Hopefully it's not too bad, but I will be doing the other ones. I don't know when. I'm not going to set a schedule, just when I feel like it. Depends on my other schedule for tutoring and other work and stuff like that. So yeah, spot on. Thank you very much, everyone. And I'll see you another time. If I can figure out how to stop the screen anyway. Stop. Right. Cheers.